Welcome back everyone. In the last class we were looking at the response of a standard first order system, which the closed loop configuration of a standard first order system looks something like this. We had found out the closed loop transfer function of the system using the formula this which we have derived in the last class, and then we saw what will be the step response of the system, what will be the steady state value of the system, and how does the error signal evolve as time changes. We saw that as time changes, it is an exponential trajectory which goes down to 0 when t is greater than 0, and you can see this here itself. So, this was equal to 0. We had also seen in a simulation that if I change the position of 1 by t, which we defined as p, which means that the transfer function of the system was written as p by s plus p, where in the complex plane, if this is the real line, this is the imaginary line, minus p is the position of the pole of this system. And we saw that as we took minus p to the left, or as we change the location of the pole away from the imaginary axis, the trajectory was becoming quicker and quicker. It was quickly going to the value of 1, the desired response. So, I had said that okay, it is the pole position that actually can help you in managing at what rate will the response go to the final state for the first order system at least. Today we go ahead from this point and look at the ramp response of the system. What happens if I give the reference input here as a ramp input? What will be the output of the system? And we already know how to find out response of a system. So, basically we will, let me just go back. So, basically what we will do is we will have to write down ys will be equal to 1 by t s plus 1 by t into rs, and since this is ramp, we know that rs in this case will be 1 by s square, because the Laplace transform of a ramp function is equal to 1 by s square. We had seen this while we were discussing Laplace transforms. So, now let us see what will be the partial fraction for this. So, let me write down the partial fraction for this. So, the partial fraction would be 1 by s square minus t by s plus t by s plus 1 by t. You can go ahead and check, this is the partial fraction that you will get, and so from here we can directly write what yt will be. Yt will be equal to Laplace inverse of 1 by s square is t minus the Laplace inverse of t by s is t plus e to the power of minus t by t to t whole into u step, because this is only for t greater than 0. So, this is what the expression would look like, and if you go ahead and plot this expression, this is what it will look like. The red line here is the reference trajectory. This is your ramp reference signal. Okay, this is the signal that we want our output to reach to, but you can see that in this case the blue line, which is the actual response of the system, never reaches the ramp. Instead, there is always a difference, there is always an error between the actual output and the reference output. Okay, we can actually go ahead and check what the error is. So, if you look at the steady state value, so I mean forget about the calculation, what will be the steady state value of the response of this system? You can see that the output in this case is always increasing. So, as t tends to infinity, the output will be also infinity, which is evident from this. You can see that if I find out limit t tends to infinity, yt, which is the steady state value of the output, it will come out to be infinity. But more interestingly, you can see that the error here is same almost, right? Almost what? This is exactly same, right, the error at a particular given point of time at say t equal to t second, what is the error between the actual and the reference? This is the value. What is the error between the actual and the reference at t equal to 8? This is the value, and you can see that it is the same, right, as we go, as we increase time. Of course, here it is smaller, but as we keep on increasing time, it is the same. So, let us see what the error is. So, RT minus YT will give you the error. So, RT is nothing but TU step minus YT expression we have just now found out, we put it there, and so we are left with T 1 minus e to the power minus t by t u step. Now, what is the final error or the steady state value of the error signal? Steady or what is known as steady state error. Steady state error means the error at t tending to infinity, that is steady state error. So, error at t tending to infinity comes out to be t, and you can see that this is a constant value, which means in the plot that we just now saw, this value is the t value that we have. Okay. So, in this case, in case of a standard first order transfer function or a standard first order closed loop system, unity feedback, negative configuration closed loop system, you can see that the error is constant for a ramp response. Okay. So, we can actually go ahead and see, let's look at this plot, and this is the response of the system. Again, I am not getting into the code. So, this is the response of the system, this is the value of p. So, pole is at 1, which means 1 by t is 1, which means t is 1 in this case. Now, as I increase the pole, you see now p is at 3.18, which means you can see this, it is at 3.18, which means t is 1 by 3.18. Okay. So, this distance is 1 by 3.18, which means it is decreasing. As the value of p is increasing, the value of t is decreasing, which means that the error is decreasing. I can keep on increasing this, and you see the error is decreasing. So, I am making it better and better in some sense, right. So, you see the position of the pole is very important, that is why. Okay. And this will play a very crucial role in understanding how does these type of systems behave. Now, till now whatever we have seen is that we have taken the system. So, where this is the plant of the system, say we have never taken the controller into consideration. Okay. But in general, our work as control engineers would be to design the controller block, the basic configuration that I had already shown you all. So, what are the steps basically? Suppose you wanted to control a system, you will first do the mathematical modeling of the system. So, when you did the mathematical modeling of the system, you came out with the plant transfer function to be 1 by st, say. Example, suppose it is a first order system, you came out with the plant transfer function to be 1 by st. And what is the feedback transfer function? Say 1. There is nothing in the feedback, you are just connecting the output directly to some error block or summer or a block which finds out the difference between the reference and the output. Fine. So, till now you had no role to play because the plant is given to you. You cannot change the plant is already there. Okay, someone gave you the plant, okay, this is the process I want you to control. So, the plant is there, the feedback path is also there already, sensors are already there, say. So, these are the things you cannot change, these block diagrams you cannot change. Now, what we will do as control engineers is that we will put a controller block here. Okay. Now, what was that controller block? If you remember, I had written k of s, right. So, what I am saying is that we do not write k, suppose it is not k of s, it is just constant, some constant number. Okay. What it is doing is, it is taking error as input, multiplying k with it and then giving that as output to the plant. This k is in your hand, you can change this k, it has nothing to do with the actual plant because this is you are creating. Now, if I put k there, what are the changes that comes in? You see the transfer function of the system, although I have already written it for clarity, I am just rewriting it. What is the transfer function of the system using this formula? G in this case is k by st by 1 plus G is again k by st and h is 1, which means this is equal to k by t by s plus k by t, and this is what is written here. And see the pole location is now minus k by t. Okay. So, when the controller was not there, it was minus 1 by t, and since it is a plant, you will not be able to change 1 by t value, it is already there. But now you see, adding this k block, extra one block, what you have done is you had brought some control in your hands. Okay. Now what you can do is you can change the value of k and change the pole position. It is almost like if you do a simulation, the slider in that I was changing, you can think of it as the k maybe. Okay. So I can change the value of k, and as I change the value of k, the pole position also changes. If I increase the value of k, you see, if I increase the value of k, of course I am assuming here t is greater than 0. So if I am increasing the value of k, that means the pole position is moving away from the imaginary axis, and as it moves away from the imaginary axis, we know that the step response of the system will become faster and faster. The ramp response of the system would be such that the errors will come down. This is what controller design is actually. How do you manipulate the poles? What type of, see, this is a very simple thing where I have just used a gain block, where I have just taken a constant which multiplies with the error signal. You might come up with something else also. We will see, of course, later on. Okay, but for now, a simple gain itself can help you so much. It changes the location of the poles. And as control engineers, this is the main idea. The main idea is to put some block here, such that it affects the pole in such a way that you get the desired output. Okay. So of course you cannot do this like, I mean, you cannot just think, oh, I will add that, I will add this. You cannot do that. I mean, you have to understand how the system behaves so that you know what to put there, so that does what you want to do. And that is what we are trying to learn in this course. Okay. So remember this basic idea. This is the basic idea of the entire course. Controller design means what should I put in that block. Okay, coming back to what we were discussing. So here you see, as soon as I put a k here, you can go ahead. I would like you all to take it as an assignment where you try to find out the step response of this system, where the k block has been introduced. The controller block, the constant gain block has been introduced, and as a result you should get the step response, steady state value and the error signal values to be these. Okay. In this case also the error will go down to 0, because you see you are just multiplying with a constant, this will go down to 0. However, the rate will be different. If k was 1, whatever rate was there, when k is more, then the rate will be different, it will be faster. Okay. Great. So now we know what controller design specifically for this example at least is, for the standard first order system it is. Now we will move to second order systems. Okay. So let us move to second order systems, and in second order systems again, like this first order case, in second order case we are assuming that the plant is of this form. In the first order case we assumed it 1 by st, now we are assuming that the plant is of this form. So GS is this, and we are assuming a unity negative feedback configuration. Unity negative feedback configuration. Unity means HS equal to 1, negative configuration means there is a negative sign here, which means the formula will be G by 1 plus GH for the closed loop transfer function. Okay. You might be thinking, why am I introducing so complicated looking symbols, zeta, omega n here. So this is called zeta, by the way, this is called omega n. Don't worry about it, it has meaning, there are reasons for it, and in standard textbooks we use zeta and omega n. You can always use ABCD, no one is stopping you to do that, it's just a name. But since the books around which are available generally uses these, in control we use these symbols, so let us stick to those symbols. Okay. Symbols are not important, the idea is important. So let us try to get the idea. What are we going to do now? So first of all, let us find out the transfer function, overall transfer function of this system. You know how to find out transfer function now. It's quite easy. So what is GS? GS is given to you. So GS would be omega n square by S into S plus 2 zeta omega n by 1 plus GH or GS multiplied by HS is 1. So this comes out to be omega n square by S square plus 2 zeta omega ns plus omega n square. So the transfer function of this standard second order system, some unity negative feedback closed loop system, is omega n square by S square plus 2 zeta omega ns plus omega n square. Something to note here is that you see in this case we will have two poles, right. Now, depending on the value of zeta and omega n, will the poles be on the imaginary axis, will the pole be on the complex planes right hand side, where will be the location of the poles, because we have two poles, of course the two poles will be complex conjugates of each other, because zeta and omega n here are real numbers. So, this is a polynomial with real coefficients. Any polynomial with real coefficients, if one of the roots is complex, the other root has to be complex conjugate. Okay. So, in this case also what will happen is, since you have the denominator here is a second order polynomial in S with real coefficients. So, the roots in this case will be on the complex plane, complex conjugate of each other. This may be like this, or they may be sitting over on the real line itself, or they may be sitting over on the imaginary axis, they may be sitting over on the right hand side of the complex plane. So, they can be anywhere, but if it is complex, then it has to be in complex conjugate form. They has to come in pairs. Okay, remember that. Now, we will link it up with the trajectories later. Okay, but first let us try to see what the step response of this system would be. We will not try to find out the ramp response for this system, because the expressions will become complicated and it won't give us much insight as such for now. At least we will talk about it maybe sometimes later if required, but for now we will just concentrate on the step response of the system. And so, let us look at the step response of the system. Now, to find out the step response of the system, so what is the first step? The first step is Ys equal to the closed loop transfer function multiplied by Rs. Rs in this case is 1 by S. So, what will you do? You will try to write it down as partial fractions. What will be the partial fractions? So, Bs by Bs plus D, Cs plus E say. So, what will be the partial fraction? There will be some terms at the bottom, right. There will be some terms at the bottom, something like this you will try to do, and I have already found out the partial fraction. So, let us see what the partial fraction will be. This will be the partial fraction. Now, one important thing here, while writing the partial fraction, we have to be a bit careful, because the value of zeta here can be anything, right. Okay. So, first of all, zeta is not negative, okay, because it does not give any physical significance to this, or there is no physical significance as such, although zeta being negative has some consequences, but that we will talk about maybe later sometimes. But for now, zeta is greater than 0. Now, if zeta is greater than 0, then also we can have many cases. So, the case that we are taking first is when zeta is from 0 to 1. Okay, you will soon understand why these cases are there, but for now let us say that suppose zeta is from 0 to 1, 1 excluded. So, zeta is either z equal to 0 or from 0 to 1, 1 excluded. So, in this case the partial fraction will look like this. Now, notice since zeta is from 0 to 1, I have written here 1 by zeta square root. So, therefore, that this term will turn out to be a real number. Had zeta been greater than 1, then I would have to write this way, so that it turns out to be a real number. Okay, that is the difference actually, and that you will see that also leads to some changes in the expressions also. So, for now we are saying zeta is from 0 to 1. Why am I taking it in this form? Because you see these two forms, the reason being that we will try to do Laplace inverse, right. If I want to do Laplace inverse, the partial fractions should look either of this form or of this form, right, when the partial fraction has quadratic terms in it. The denominator has quadratic terms in it, because the Laplace inverse of this is sin omega and the Laplace inverse of this is cos omega t, right. So, that becomes easier for us. So, that is why we are writing it in this form, and you can see that once I write it in this form, things will become much easier now. So, let me just go one by one. So, there are some mathematical juggleries that will be done here to get to a nice form. Okay. We always try to get to a nice form, because if you go to a nice form, it is easier to analyze the expressions. Okay. So, the steps that I am going to follow now, you can just keep an eye what I am doing. It is just mathematical jugglery that I am doing here, okay, to get to a nice form. So, this term and this term remains the same. Now, this term you see, this is like s square, s plus something whole square plus say omega square. So, I will try to get an omega here. So, that is why I am writing this term over here, but since I am writing something extra, I am also removing this with the writing it in the denominator also. So, I have not changed much, you can see that. Now, what I do is just to shorten things up. So, I write omega d equal to this, although this has a physical meaning, we will come to that later. So, omega d equal to omega n root over of 1 minus zeta square. So, this I am replacing with omega d. So, then you can see that this becomes s plus zeta omega n by this. I am replacing this by omega d. Here also this term I am replacing by omega d, this term gets replaced by omega d. However, I am not replacing this term as with omega d, because this one and this one will get cancelled out. So, hence I am not writing that. Now, once that cancels out, you see what I get if I do a Laplace inverse. So, this becomes 1 by s. Now, what about this term? This is s by s square plus omega square, but the s has been replaced by s plus zeta omega n. So, we have e to the power of minus zeta omega n t because of that s plus zeta omega n term, and then rest of it is just cos of omega dt. Similarly, for this part it will be e to the power of minus zeta omega n t sin of omega dt, and the factor here is zeta by root over of 1 minus zeta square. Okay. All this is true for t greater than equal to 0. I have not written u step because keeping on writing it all the time, it becomes difficult to follow keeping it in the expressions. I am just remember that I am writing this expression for greater than equal to 0. Great. So, we have this expression now. Remember, this is the change that we have done. We have replaced omega n root over 1 minus zeta square by omega d. Now, we do another trickery, where what will we do is we will take out 1 by root over 1 minus zeta square, and this is what we are left with. So, from here remember, this also can be taken out, these two terms can be taken out to the left. So, now before that I am defining cos of phi to be zeta, again a new variable I am introducing, phi. Okay. So, cos of phi is zeta. So, if cos of phi is zeta, sin of phi will become root over of 1 minus zeta square. So, here this is sin of phi, this is cos of phi, e to the power of minus zeta omega n t can be taken out. I have taken it out now, you can see this. So, I am left with this, and this is just a standard sinusoidal formula, which is sin of omega dt plus phi. And you see, this looks so neat, it is a neat expression, y t equal to 1 minus e to the power minus zeta omega n t by root over 1 minus zeta square sin of omega dt plus phi. This is the expression. The variables are the two new variables that I have introduced is omega d and cos phi equal to zeta. Now, let us try to plot this. Let us see how does it look. Now, this I can divide into 4 parts. So, this part I will plot first, okay, and then I will plot this part also. After that, I will plot these two multiplied together, how does it look, and then finally 1 minus the entire expression. So, let us see. So, you can see from this expression itself, this will be a exponential trajectory which dies down. Okay. I have plotted this for some value of zeta and omega n. Zeta is from 0 to 1 and omega n I have chosen something, okay, to plot it. You can try it on your own as well, okay, plotting it. So, this is e to the power of this is an exponential envelope. Then we have, see, this is a sinusoidal term, okay, where the frequency is omega d. So, here this is omega d. So, this is the frequency, and phi is given by cos phi equal to zeta, and so basically it is a sinusoidal function which has a phase in it, and this is how it looks like. Now, when I multiply these two, if I pointwise multiply these two, this is what I will get. So, you can see that it is a damped oscillation. There are oscillations, this was the oscillation, but it is damping down because of this exponential term. When it multiplies, we are getting a damped oscillation. Okay. So, this is the multiplication of these two functions, and then finally, the final expression is 1 minus this. So, this is what it looks like, right. So, you can see that this is there is some damping. So, it was trying to oscillate, but it damped down, and at the end it settled at yt. So, if you try to find out limit of t tending to infinity y of t, you should get 1 from this expression, because you see at least the simulation says us that. Okay. Now, we move to the case when zeta is 0. So, remember the previous expression is valid for from 0 to 1, 0 included. So, just for the special case of zeta equal to 0, what happens? So, if zeta equal to 0, what will happen? Omega d will be equal to omega n, and you see phi will be equal to 90 degree or pi by 2. In that case, what will be the response like? So, since zeta is equal to 0, so this entire thing goes to 1, and then this term will become, this is pi by 2, and this is omega n. So, sin omega n t plus pi by 2 is cos omega n t. Okay. I hope you could follow. So, you see what I have done is sin of omega d has become omega n now plus pi by 2, and what is this? This is cos of omega n t. So, 1 minus cos of omega n t. What will be the response like? You see this term goes to 1 and this term goes to cos omega and omega dt. So, this is the response like, and so this entire term is nothing but again cos of omega n t. This is how it looks like. So, 1 minus cos of omega n t is this. So, which means that when zeta is 0, then you have oscillations, complete oscillation, no damping is there. But when zeta is from 0 to 1, 0 not included, then there is a damping. It is oscillating, but it is damped oscillations. In this case, there is no damping. And what is the frequency of this oscillation? Omega n. Okay. Next comes the case when zeta is equal to 1. So, when zeta is equal to 1, so let us see how the things change. So, if zeta equal to 1, we can substitute 1 here and we will take Laplace inverse of, in place of R s we have 1 by s multiplied by this term. Now, the denominator here is a perfect square. So, we can write it down as s plus zeta n whole square. You do a partial fraction and the partial fraction of this terms will come out to be this. You can cross check this, and finally, the Laplace inverse of these terms will come out to be of this form 1 minus e to the power of minus omega n t 1 plus omega n t. So, now let us look at how does this response look like for the case when zeta equal to 1. So, you can see that e to the power of minus omega n t is nothing but a function of this form, where it is an exponential function which decays to 0 as t tends to infinity. 1 plus omega n t is kind of a ramp function with a plus 1 added to it, and then if we find out 1 minus these two terms product, we will get something like this. Now, one thing to notice here is that this response is increasing. However, you see there is no overshoot here. Okay. In the previous case we had overshoot, but here there is no overshoot, and one more important thing to notice is that there is a U shape kind of a thing here. So, you will see that this thing will not remain when we go for the case when zeta is greater than 1. For zeta greater than 1, again the expressions will now see I am writing it as zeta square minus 1 instead of 1 minus zeta square. I am writing it as zeta square minus 1, because now I will write root over of zeta square minus 1 now that zeta is greater than 1, just to avoid the complex terms. Okay. So, in the previous case I wrote root over 1 minus zeta square to avoid the complex terms. Here also I am doing the same. I am writing it as root over zeta square minus 1 to avoid the complex terms, because zeta is greater than 1. Again, you do not have to remember all these things. This is just basically I am just trying to show you what the expression will look like. So, you see y t will be looking like this, and now in this case you have 3 terms, and all these 3 terms, let us see how they look. You see this term is an exponential term, this is also an exponential term. Okay. So, these all are dying down, okay, and when you do 1 minus these 2 terms, this is what you get. Notice that there is nothing like this as was the case in zeta equal to 1. So, it is starting directly from this point. So, as a whole these are the 4 cases that we got. Okay. The more interesting ones are from zeta equal to 0 to zeta equal to 1 actually. For zeta greater than 0, you will always get an exponential trajectory, okay, of this form. But for these 3 cases, this is the part where it will become important for us to understand this part better. Okay. And you see in the expressions, what did we get? Here we got oscillations, here it was, here we had oscillations, here we had damped oscillations, okay, as t was going to infinity. Here it was going to 1, but like this, okay, and here it was a completely exponential trajectory, something like that, 1 minus an exponential trajectory going to 1. In all the cases everything is, this one was also going to 1 like this. In every case things are going to 1. So, in this case we had oscillation, so we call it undamped, in case of zeta from 0 to 1, it is under damped, it is not completely damped, because the oscillations are damping down, but there are oscillations, so it is under damped. Zeta equal to 1 is critically damped, that means you have reached damping, and for zeta greater than 1 you will always get a damped oscillation. There will be no oscillations as such. I mean, you will never get a damped oscillation, it will be completely without any oscillations. So these are the 4 cases that we got. So for zeta equal to 0, it will be only oscillations undamped. For zeta from 0 to 1, we will have underdamped, that means there will be oscillations, but it will damp down soon. Then we will have a case which is basically the borderline of fully damped and underdamped. Okay, so that is critically damped, zeta equal to 1 case, and when you go greater than 1, then it is fully damped, or it is called overdamped. Okay, these are the 4 cases, and you can see that in all these 4 cases zeta is playing a role, because zeta is the one which is controlling the damping of the output, and that is why zeta is called the damping factor. And remember the oscillations will have some frequency, because the expression was sine of omega d t plus phi, right. So omega d has a name, and omega d is called damped oscillation, because for the damped case, for the underdamped case, we had sine omega dt, right. So this omega d is called damped oscillation frequency. Okay, but when we had no damping, it was undamped, then the frequency is called natural frequency. So without any damping, whatever frequency the output has, this we are calling as natural frequency. So we got 3 important terms here: omega n, omega d and zeta. Okay, and these will be very important for us as we move forward. We will link it up with poles, and we will also see how does this response evolve as we change the location of the poles, like we did in the first order case, and that we will do in the next class. Thank you.